And it is my pleasure to introduce our speaker today. Our speaker is Jasmina Djordjevic from both University of Oslo and University of Niš. And also it is my pleasure because she will talk about our joint project. So please, Jasmina.
Thank you, Andrei, for the introduction and also for the organizers for inviting me and giving me this nice opportunity to present this ongoing work with Professor Andrei. So today I will talk about backward stochastic differential equations with interaction. And my talk will consist of 3 parts, actually, where in first 2 parts I will give some preliminaries about backward stochastic differential equations, shortly called BSDs, and the equations with interaction in general. And then I will present the main idea for BSD with interaction. So maybe some of you will be familiar with the results from first 2 parts, but because the ideas which are repeating, I will say the line of the proof and the ideas. So BSDs were introduced in 70s by Bismuth and Kusher, and later on some additional results were given by Benson and Hausmann when they solved the stochastic optimal control problem. So what they did, they wanted to find the maximize or minimize condition for this condition in last line for the forward SD given in general form, which drift and diffusion depend on both processes X and U, which is now additional control process, and X has initial condition X0. In the value which we want to optimize, the function L is dependent of both processes, X and control process U, while this function phi is actually measurable with respect to filtration in final moment, and it has growth at most than as X squared. They solved, sorry, I can go, okay. So just a second, sorry. So they solved this problem via maximum principle. So they define Hamiltonian for which they imposed the sequence of maximum conditions. And in one of them, actually BSD occurred. This is this differential with respect to process P, and it has a final condition. So after all, many authors tried to generalize this equation because in this condition, only linear form of BSD occurred. And the first one who gave the existence and existence uniqueness result were Perdue and Peng in 90s. So general form of BSD is given in this box, and it actually has a drift and diffusion, which are of general form now. And the condition is that it has, the Y has a final condition, and the solution is given with the pair of processes, Y and Z, where the Y is called the state process, while the Z is called control process, where the role of process Z is to lead process Y in a value Xi in a final moment capital T. Notation for spaces L and MR are given as usual. And I will just like to emphasize one more application of this BSDs, and it is application in pricing European option in complete market. So if capital T is an exercise date of an option, if then Xi can describe the payoff, R is interest rate, and theta is risk premium. Then the arbitrary price of European option is actually the state coordinate of this solution of a given linear BSD. But as the price of an option is under continuous effect from the market, it is more natural to observe some kind of a perturbation of this equation in order to describe better its price in accordance to the state of the market. So we have observed the problem with when the payoff price is perturbed, arbitrary, as well as drift and diffusion coefficient. So we introduced some functions alpha and beta perturbed, which are dependent of the solution, as well as some small value epsilon. So now this equation is of nonlinear form, and it is hard to solve it even numerically. So that's why the interesting problem is, which we analyzed, is to observe the closeness of the solutions with respect to the size of perturbations. And as this is the application in pricing of an option, we observed also in a case when the arbitrary prices are close with a given boundary of the closeness, how wide will be the time interval of the given closeness. So for this theorem of existence and uniqueness, we need just some introductory hypothesis. So H0 is the one which is referred to the conditions on final value and the drift and diffusion coefficients. So final value size from space L2. Functions f and g are defined in a given way, and they're measurable with those products. And furthermore, for every t and zero value for y and z, f and g are from M2. So now formal definition of the solution is a pair of processes YZ, such that if for every value t, y, and z, f and g are from M2, and if this pair of processes satisfy equation almost surely. And the solution is unique if for any other solution y bar, z bar, those two expectations are 0. So actually the expectation of the square of the difference and R is 0. So Perdue and Penck in the same paper when they introduced this BSD gave the existence and uniqueness result under Lipschitz condition for function f and g, which is given with hypothesis H1, but later on many authors weaken up this condition. So there is a sequence of papers for the existence and uniqueness under different version of the non-Lipschitz condition. So I will just give a line of the proof, which consists of 4 steps. And in first step, the basic BSD is observed, where drift is deterministic function, and in diffusion, in addition to the control process, we have some other deterministic function G. And the proof of existence and uniqueness of the solution for this equation relies on martingale representation theorem. So if we define y of t to be conditional expectation of a given difference, then there exists z bar from M2 such that conditional expectation can be expressed as an initial value for y and integral from 0 to t of process z bar with respect to Brownian motion. And if we take that z bar can be expressed as the sum of z plus some function g, the result is directly proved. Further on, if we generalize this equation in a sense to introduce control process in the drift function, so proof of uniqueness goes in that way that we first apply Ito formula on the difference of 2 solutions, if we suppose that there are 2, and then apply elementary inequalities. So we can move this member if we took because the constant is less than 0, we can move it on the left side, and directly from Gromwell-Leva, we have uniqueness of state processes, and further on uniqueness of Z processes. For the existence, Picard iterations are used. So for initial step, Z0 is 0, and iterating step for Yn is and Zn is given in last line, where now because of the defined iterations, drift is familiar. So this equation has a solution with respect to first step. So the sequence is well defined, and what is left to prove that it converges. So we just take a difference of the successive members and then apply Ito formula on its square, take expectation, And after elementary inequalities, we have this inequality 1, where after introducing notation that AN is actually expectation with respect to difference of state processes, and BN expectation of difference of control processes, we can simplify this inequality 1 to the form 2. And its integral form is given in the next line, where each of the members of the left sign can be bounded with the term on the right, where after iterating it n time, we have that these inequalities in last line hold. So further on, as this differential of an plus 1 is non-positive, then we have directly then bn plus 1 in time 0 can be estimated by this sum, where we already estimated n plus 1 0 with this term. And then iterating again for the Bn until first step, we have that this inequality holds, which enable us to actually state that Yn and Zn are Cauchy sequences in M2, and actually the existence result holds. In next step, the equation is generalized even more. Now the drift coefficient is fully dependent of processes of solution, and function g in diffusion coefficient is now also dependent of state process. And uniqueness is proven in similar way as in step 2, so I will not repeat it here. But for the existence, the iterations are defined in a different way. So now y0 is 0 for every t, and yn is given with this iterating step, where now this is equation of the form given in step 2. So again, its solution exists. So it is enough to prove that it converges. And in a similar way as in step 2, we have obtained this inequality. And now we define only process A of n because it's enough. So we reduce it to the differential equation with the final condition 0, where after iterating it n steps, we again have the convergence and the statement that Yn and Zn are Cauchy sequences. And at the end, the full BSD, which has general drift and diffusion, is in the step 4, and its solution is proved using the steps 1 to 3. So I will not repeat the ideas here. So after this equation, I would like just to say that there are many other versions of BSD, so-called backward-doubly stochastic differential equations, which has 2 Brownian motion, then reflected backward stochastic differential equations, Volterra, etc. So a wide interest for observing these equations has occurred after 19th.
Nina, can I interrupt you just to say a few words about new features which this equation have comparatively to usual ordinary differential equation? So first of all, we use Clark representation theorem with respect to the Brownian filtration. And secondly, in one step, we use Ito formula for backward stochastic integral. Am I right?
Yes, this is actually all.
So these are 2 new features which we have comparatively to the ordinary SD, yes?
First one which you mentioned here, and the second one actually when we apply.
Okay, let's go.
And also in comparison to the forward SDs, this equation have parallel processes and as its solution, as I mentioned a few times.
Yes. Okay.
So in second part of my talk, I will say a few words about equations with interaction in general. So first about notation, let us suppose that we have the main phase space RD, that then sequence of RD valued binary processes, measure mu0, And then stochastic differential equation with interaction, which was introduced by Djordjevic in 2002, is given in this form, where now we have a general drift dependent not only of time, but also of measure and solution. And the same holds for the diffusion coefficient. This equation has initial value u, and measure mu t is actually an image of initial measure under the mapping x. Furthermore, the solution of this equation, x in some moment t, is trajectory, can be seen as a trajectory of a particle which starts from point u and which in some moment t interacts with other particles, where mu t actually contains the information about these interactions. Okay, for the proof, we need to introduce Wasserstein distances given by Dudley in 1998. So if this calligraphy M is a space of probability measure on the complete separable metric space X row, then furthermore, for two measures from M, we will denote with the C the set of all probability measures which have mu and ni as the marginal projections. Then Wasserstein distance of order 0 is given with the infimum over this double integral, where M and gamma 0 is a complete separable metric space. And similarly, the Wasserstein distance of order n is defined with this expression, and together with Mn, this also is a complete metric, separable metric space. And first, some simple example. If we suppose that there is no diffusion and that the drift coefficient is represented via integral over some function f with respect to measure mu, where f is a bounded and continuous function. Furthermore, let initial measure mu0 be discrete, and they're given as a sum from for k from 1 to n, pk delta uk, where pk are positive probabilities, and every point is reachable, where y1 to in are different elements from Rd. Then measure mu t as an image of initial measure under solution x in some moment t after moment 0 is given with this sum. And equation with interaction with discrete measure reduces to the equation given in the box in the end of the slide. So it has a simple drift given with the sum and initial condition u. Furthermore, if we simplify it further, so if we introduce that xk of t are the values of x with a final condition uk in moment t, then we consider actually the trajectories of heavy particles, which end in these points uk for k from 1 to n, and they interact with other particles where this interaction is described with function f. So now this equation reduces to this form, and it has one disadvantage. This is that this function f actually represents the interactions between two particles, so pairwise interaction only. But this can further be overcome if the drift has more general form. So actually with this expression, where now f and if in this simpler formula f tilde gives the interactions, describes the interactions between all the particles. So between all n particles in this system of n particles. So the definition of this solution is given now in this slide. So if for any initial measure mu0 and functions coefficients a and b, solution is random field X, such that for any u from RT and any moment t, restriction of X on any interval 0t is actually measurable with respect to this product, and even more, for every u and t, integral form of this equation also holds. Theorem is proved under condition that, first of all, coefficients A and B are continuous with respect to X, mu, and T, and they satisfied some version of Lipschitz condition with respect to Wasserstein distance of order 0. So for any U1, UT from RT and any two measures from M, this inequality holds for coefficients A and B. If this holds, then there exists a unique solution of equation with interaction. And the method, the solution goes via method of successive approximations. So we have that in initial step, in x0 has value u, and measure in initial step is initial measure. Then iterating step for x1 is given with this equation, where now in drift and diffusion, actually mu0 is known. So the coefficients only depend of x1. So this equation has solution by standard theory. So in order to continue with these iterations, we need to show that actually mu1 and later on mu_n will be measures. So for this, we prove that x1 actually has a continuous modification. And this enables us to state that mu_t1 actually is a random measure. So in this way, we can continue with iterations for x2 and further on. And by this, we have two sequences, one of random fields and one of measures. And now what is left to prove that this sequence converges. So I will not go into details here, but we have applied Grunwald lemma in last inequality and defined this auxiliary function. We have at the end that those two sequences actually converge. So we have the existence of the solution. And one more thing which is important here to emphasize, that those equations with interaction describe mass evolution, and their solution has the advantage with the comparedness to the passive trajectories, which are observed in stochastic flow theory. And more about this can be found in papers which I mentioned here by Drogostev, Karlikova, Professor Pilipenko, and myself. And now I would move to the main part, which is actually BSD with interaction, where we now know something about BSD in general and equations with interaction. So on complete probability matrix, on the complete probability space, omega fp, and now we have spaces M2 as before, with the difference that now they have first coordinate to be filled. So BSD with interaction is given in D4. It has drift, which is dependent of time measure and state process of the solution. It has final condition. And the measure mu_t in some moment before capital T is actually an image of a final measure under a mapping of state process Y. And again, now the trajectory, actually the trajectory of the particle can be described by the Y process, which actually describe that this particle ends in point U and that it contains in some moment T before this reachable point, it contains mu_t informations about the interaction with other particles, which end in some other final points. So let function f be defined in this way. Then we can formally define the unique solution of BSD with interaction. So it is a pair of random fields from n2 square m2, such that with final measure mu t, and for any final value from RT, if this pair of processes satisfies equation almost surely. And the uniqueness is defined in the same way as for the ordinary BSD. So if we have two solutions, then those two expectations are zero, then the solution is actually unique. We will restrict ourselves to the case when drift function f can be represented as an integral of function h with respect to measure mu t. And first, we'll prove the existence for the simpler example. So in case when we have discrete measures, so if a final measure mu t is a discrete one, so given with the sum, then measure mu t in some moment before capital T has a form of this sum, where UKs are now final conditions for any k of 1 to n. So BSD with discrete measure for heavy particles, because we restrict ourselves to the case of final conditions UK, has form given in the box here at the end of this slide. So it's actually its drift is given with the sum of functions h, which describe pairwise interaction between those particles. To prove the existence uniqueness for result for this equation, we need the Lipschitz condition for function h. And then we can state that there exists a unique solution. Uniqueness is proved in a standard way. So if we suppose that we have two pair of random fields which satisfy BSD with final discrete measure for heavy particles, then if we take integral form of those equations, subtract them, and then apply square and expectation, we will have inequality as this one. So further on, we will sum all those inequalities over k goes from 1 to n. And if we want to simplify this expression, we will just introduce notation a of t to be the sum of expectation of square differences of processes u and u bar. And now directly from Gronwon lemma, we have that uniqueness of solution holds. Yes, Andre, you wanted to say something?
Yes, I want to say that maybe AT is less or equal than C small integral from T small from T capital.
Okay.
Here, when you just write the equation for AT.
Okay.
It must be, we forgot it, it must be from T small to T capital here, yeah? Am I right?
But it depends how.
Not here, in the next line.
Yeah,
Next, here, AT.
Yeah. Okay, I first understood you that you mean that the definition of AT different. Yes, you're right.
No.
Yes, here has to be, but again, as A is positive, this also is true because we can.
Yes, it is also true, but we have to apply Gronwon lemma. So it must be a small t, yeah.
Yes. Mm-hmm. Okay, then for the existence, we will have iteration steps. For initial step, y0 is 0, and then iterating step is given in this way, where now for I plus 1, we have that drift is completely familiar. So actually the solution of this BSD exists because we already discussed it in the first part that this BSD has a unique solution.
So this is a basic BSD which was written by Pardue and Penn, yeah?
Yes.
Just multidimensional. Is it correct? So just
yes.
this.
Yes.
Yeah.
And then taking in order to prove that this converges, let us take expectations similar as in uniqueness part of the difference, and then applying some elementary inequalities, summing up all of those inequalities over k, going from 1 to n, because we have a case of heavy particles. We have this inequality in last 2 lines, which we want to estimate further on. So denote AI and BI with the sums with respect to difference of state processes and control processes. Our last inequality reduces to this differential form, which is in integral form given here. And again, as before, we have that these are Cauchy sequences in M2 times M2. So the existence is proved. Now, if we want to generalize the case of BSD with a discrete measure, in the sense that we now have any final value from RT, we will actually use the fact that this process, which occurs in the drift in the function h, is actually a function of BSD with the final discrete measure, and for heavy particles, which its existence and uniqueness we proved in previous theorem. So theorem 2 gives the statement that this BSD of form 3 with the generalization with any value in finite moment t has a unique solution. So as this equation 3, because of the arguments which I just mentioned, is of the
Nina, can I just say that very good comparison now that here particles now determines the destiny of all other particles, yes? But here there are much more freedom as comparatively to usual stochastic differential with interaction, because together with process Y, we also have to define process Z. So at least we can say that the light particle have 2 features, Y and Z. Yeah.
Yes.
Mm-hmm.
And this equation 3 is actually of the form of equation 4, which we already discussed in part 1, that has a unique solution. So as a consequence of this, our equation 3 has a unique solution. Now, next step would be to generalize this BSD for any measure, not only discrete one, in a finite moment. So actually to have this full version of BSD with interaction. And for this, we will use approximation that we will suppose that any final measure mu t can be approximated with a discrete measure. And before this, we need some auxiliary results. And first lemma is a lemma which gives some kind of Lipschitz condition for the drift with respect to Wasserstein distance of order 2. So for any y1 from RT and any 2 measures from M2, we proved there exists constant positive constant C such that this inequality holds. So if we estimate the distance, then subtract this member with integral with respect to function h, which depends on y1 and v, then applying elementary inequality and Lipschitz condition for function h, we have the last line, which holds for any kappa, and directly from Cauchy-Schwarz inequality, the lemma is proved. Second lemma is actually a very important one, and it's some version of stability result. So if we suppose that we have 2 BSD of a general form with final conditions y1 and y2 and different drifts, in accordance to that different solutions, then the difference of their solutions satisfies some kind of inequality given in this line. So it is bounded with respect to final conditions as well as the Wasserstein distance of order 2. The proof relies on similar steps as before. If we take integral forms, apply to formula on the square of the difference, we have the expression given at the end of the slide, where taking expectation, we cancel the last line, and applying as usual estimates, we have that this inequality holds, on which we can apply directly Gromov-Bell lemma and state the result. And now the main theorem, which gives the existence uniqueness to the solution of BSD with interaction in general form. So let us suppose that we have a sequence of random fields yn and zn, which solves the sequence of BSDs with discrete final measure for heavy particles, and we have a pair of processes, a pair of random fields which satisfy the BSD of general form. And if we suppose that all of those equations have same final condition, furthermore, that we can approximate actually this random final measure with this sequence in a sense of Wasserstein distance of order 2. Then those two limits hold, which have as a consequence that actually BSD with interaction of general form has a unique solution. As we saw from previous lemma, that actually
Jasmina, could you please explain us why mu t is image of measure? Okay, mu with capital T is image of mu with small t when we...
No. Mu small t is an image of mu of capital T.
Yes, correct. Yes. How to see it?
Well, how I understood it, let me just go here. So I had stated here this. So we have some final measure, mu t. And
okay, you proved convergence of mu n and you proved convergence of yn. And the question is why mu t is image of the final measure.
Sorry, can you repeat, because you are referring to this part, if I understand you well?
No, this part is clear, but you have to verify that mu with small t and y with small t have special representation. That
yes, that mu small tn is an image of mu capital Tn under the mapping yn.
Yes, no, for mu n it is clear, but the question is mu without n for
mu t, mu capital T.
No, not for mu
small
capital, but for mu small, but without n. And Andrei, see, we prove the convergence also measure-valued processes mu n t small.
This is actually the first step. That's why I
yes, exactly. Then when we have convergence of the yn to y and images of the measures to some measure under this mapping, we can just reduce the problem to the deterministic problem. And in this case, we can check that all integrals, for example, from the Lipschitz functions coincide. Yeah.
Do you have some measurability of y?
Yes, and we check somewhere before Nina showed the slide. Yes, and even before, here is it. Maybe here you see this second moment. It is estimated through this u1 minus u2 in square. So, for example, if you have the same measure, then you can have, this is semi-martingale, so you have the same not only for the second moment, but for the any moment, so it is even continuous with respect to you and so on. So
I see.
it's okay.
Can I continue then?
Yeah.
Okay, so actually the proof relies on this lemma. So as now Andre also explained, and what I wanted to say also is that actually we have here dependence of the distances in some moment before capital T. So we have to estimate this distance in terms of distance of final measures. So in final moment capital T. So by definition, we have this inequality, and using elementary inequalities, we are left with the expression given with equation 5, where now we have to estimate separately these two members. And for the first member, we see that we have the same final condition, and only what changed here is the measure, μn and mu. So actually from lemma 1, we are, this expectation is only bounded with the distance, Wasserstein distance over the integral of Wasserstein distance. And for the second member, we will first estimate this expectation within integral. And here we have the same measure and the different final condition. So again, from the same lemma, we have that this can be bounded with the difference of final conditions. If we substitute now those two estimates in equation 5 here, by definition of Wasserstein distance for the second member, we actually have that this is the distance in the final moment capital T. And then by applying Grunwald lemma, we estimated the distance of measure in some moment before capital T with the measures, with the final measures. And if they are close, then we can say that also the measures in previous moments are close. So from last and lemma 2, which we analyzed, we have that those expectation converges. So let me just go back. So this to 1. And because it is the same final condition, and we are just left with Wasserstein distance over the 3 or over the 2, sorry. And from this, we have also the uniqueness and existence result for the general BSD. So this is the only case we observed until now. I would just like to mention references which we used. Some of them were already mentioned in the presentation. And thank you very much for your attention. This would be all for today's presentation from my side.
Okay, Jasmina, thank you very much. And maybe somebody have questions or comments, please.
Jasmina, in one lemma, you have proved inequality, I think lemma 1 or no, before, yes, in lemma 1, yeah, in lemma 1.
Okay.
In lemma 1. So that if you have an integral functional, that integral functional satisfies this Lipschitz condition. But if you have a drift with these properties from this lemma, like Lipschitz property of function f, can you prove existence and uniqueness of solution of backward stochastic differential equation?
So if it's not of this form, but if it's
if it is not of this form, but just satisfies this this inequality.
But yes, because we have a sequence which is for heavy particles. So if we have that H satisfies, but actually we
no, the equation is another. Assume that your interaction for heavy particle not a linear like in your model, but just f of y mu.
Okay.
function f is Lipschitz continuous in this sense,
Yes, yes, I understood. Yes.
then probably you can prove also existence and uniqueness.
Yes, yes, I agree, because we can now use what we already proved for this particular form of f. So
Mhm.
we,
So actually you proved a more general result.
no, we didn't prove it still, but I think that your question has a point, that this is what we want to observe
Yeah.
later on, to generalize the
This inequality you need for the proof probably.
Yes, yes, yes. We would need this, but we can have that f can be more general, actually. Yes, and what I also think that we can even more generalize the diffusion coefficient, in the sense that we can have, as in case of BSD, some additional function g, which would be dependent of state process, and which would also satisfy some this version of Lipschitz condition, actually.
And I have one more question. If you consider usual stochastic differential equation with interaction, then as a function of a spatial parameter, then this mapping is diffeomorphism. And what about yut as a function of u in your case, in case of BSD?
Well, we didn't still, I cannot answer this now because I haven't thought about this actually. But I can think about it and I can come back to you with some possible answer. Maybe Andre, if you have some intuition, but.
And if function h is continuously differentiable or infinitely many times differentiable, probably it is possible to prove that y is differentiable with respect to u.
Yes, but we didn't still prove it, but I suppose that it should be possible to prove. But I believe that the proof will not be the same as in forward case because of this final condition and measurability. So it has to be checked, actually.
Okay, thank you.
Okay, maybe some other question. If not, I also have a comment. Of course, we will look about the more general drift coefficient, but actually my plan was to solve some control problems for ordinary stochastic differential equation with interaction. It is desirable to have to optimize some functional from mu t, from the measure mu t at the final point. So maybe we will pay attention to this problem more. But of course, the drift can be generalized. Relatively to this is relatively to the choice of equation. So it is interesting to to do fastly the part devoted to the existence of the solution, and I hope when Nina will came to Kiev, we began to work on the control problem to stochastic differential equation with interaction. But relatively to the question whether it will be diffeomorphism, I must say that maybe a technical estimators which we need for diffeomorphism we can get this continuity. What must be clarified more precisely, this grows at the infinity. Because in order to have diffeomorphism, we have to apply some topology. Not only that this is continuous differential function. For one-dimensional case, maybe we can do this, but for multi-dimensional case, we have to think and we have to check. We have to check precisely. This is rather, I think that it can be rather new question comparatively to ordinary differential equations. Hope we will back next semester with control problem for stochastic differential equation with interaction. Okay, so if there are no any questions, Jasmina, we thank you again, and we are waiting for you in Kyiv. Also, Georgi, do you know who will be next speaker?
Екатерина Глинина.
Okay, okay. So bye everybody, and see you next week.
Bye.
See you, bye.
Thank you for interesting talk. See.
Thank you for the invitation and see you soon, hopefully.
Bye.
Bye.
Bye.